So let's start by unraveling the basics of a Y connection. Have you ever looked up at a power pole and wondered how all those wires work together? Many of them use a special setup called a Y connection, which looks like the letter Y. It's actually one of the most common ways to connect three-phase electrical systems, which are, the backbone of our power grid. Think of a three-phase system as having three separate sources of electricity, or windings. In a Y connection, we take one end from each of these three windings and join them all together at a single central point. This special meeting place is called the neutral point. It's the heart of the Y configuration and is incredibly important for how the system functions, providing a common reference for all three phases. Let's visualize how this looks on a diagram. Imagine drawing three lines that all meet in the middle, just like the letter Y. Each of the three arms of the Y represents one of the system's windings. The other end of each winding, the one not connected to the center, is where we attach our main power lines. These are often labeled as line 1, L1, line 2, L2, and line 3, L3. These three lines are what carry the electrical power out from the source, like a transformer, to our homes and businesses. The central point where they all meet is connected to a fourth wire, which we call the neutral wire. This setup gives us a four-wire system, three hot lines, and one neutral. The neutral point is the secret ingredient that makes the Y connection so versatile. Because it's connected to all three phases, it acts as a stable reference. In a perfectly balanced system, where each phase is doing the exact same amount of work, very little current actually flows through this neutral wire. However, the real world is rarely perfect. If the loads on the different phases are unequal, the neutral wire provides a safe path for the unbalanced current to return to the source. This helps keep the voltages across each phase stable and prevents potential damage to connected equipment, making the whole system more reliable and safe for everyday use. So, to put it all together, the Y connection is a fundamental method for organizing three-phase power. It involves connecting three electrical windings to a common neutral point, creating a star-like shape. From the other ends of these windings, we run three power lines, L1, L2, L3, and a fourth neutral wire. This simple yet clever arrangement forms the basis for much of our modern electrical distribution network. It's a design that offers a great balance of efficiency, safety, and flexibility, which is why engineers rely on it so heavily to power our world, from giant industrial motors to the lights in our living rooms. It's a foundational concept in understanding how electricity gets from the power plant to you. Now that we understand the basic shape, let's talk about the electricity flowing through it. In a Y system, we actually have two different types of voltage to consider: phase voltage and line voltage. Phase voltage is the electrical pressure measured from any one of the main lines, like L1, to the central neutral point. It represents the voltage across a single winding. Line voltage, on the other hand, is the voltage measured between any two of the main lines, for example, from L1 to L2. Because the phases are offset from each other, the line voltage is always higher than the phase voltage. In a balanced Y system, the line voltage is precisely 1.732, the square root of 3, times the phase voltage. This relationship between line and phase voltage is a key characteristic of the Y connection. For example, if the phase voltage in a system is 277 volts, the line voltage would be 277 multiplied by 1.732, which equals approximately 480 volts. This is a very common voltage combination used in commercial buildings in the United States. This mathematical link is super handy for engineers because it allows them to design systems with multiple voltage options available from a single source. It's a simple rule. Line voltage equals phase voltage times the square root of 3. This predictable relationship makes calculations and system design much more straightforward and reliable for everyone involved. When it comes to current, things are much simpler. In a Y connection, the current that flows through any one of the main lines is exactly the same as the current flowing through its corresponding phase winding. This is because there is only one path for the current to take from the winding to the line. So, if you measure the current in line 1, it will be identical to the current in phase 1. This makes monitoring and calculating current loads very easy. Unlike voltage, There's no complex multiplier to remember. We can just say that line current equals phase current. This direct one-to-one relationship simplifies the process of protecting the system with fuses or circuit breakers. So, how do we calculate the total power in a balanced Y system? Power is the rate at which electrical energy is used, and we can figure it out using a straightforward formula. The total three-phase power is equal to the square root of 3 multiplied by the line voltage multiplied by the line current. The formula looks like this. Power equals the square root of 3 times line voltage times line current. This simple equation lets us calculate the total power delivered by all 3 phases combined. It's an essential tool for engineers to ensure that transformers, generators, and wires are correctly sized for the job they need to do, preventing overloads and ensuring efficient operation. Section 3. The pros and cons. Why we use the Y connection. One of the biggest advantages of the Y connection is how easy it is to ground the system. The neutral point provides a perfect single point to connect to the earth. Grounding is a critical safety feature in any electrical system. It helps to stabilize the voltage and provides a safe path for fault currents to flow in case of a problem, like a short circuit. This can prevent dangerous electric shocks and protect equipment from damage. This ability to create a solidly grounded neutral is one of the primary reasons why Y connections are so widely used in distribution networks that supply power directly to consumers. Safety always comes first, and a grounded Y helps ensure it. Another fantastic benefit is the ability to power different types of loads from one source. Remember how we have both line voltage and phase voltage? The higher line-to-line voltage, like 480 volts, is perfect for running large, powerful three-phase motors in factories. At the same time, the lower line-to-neutral phase voltage, like 277 volts, can be used to power single-phase loads like lighting, computers, and other smaller appliances. This dual voltage capability makes the Y connection incredibly flexible and cost-effective, especially in commercial and industrial buildings where you have a mix of heavy machinery and standard office equipment. It's like getting 2 systems in one. The Y connection also places less electrical stress on the individual windings of a transformer or generator. Because the voltage across each phase winding, the phase voltage, is lower than the line voltage, the insulation required for each winding doesn't need to be as robust. For a given line voltage, a Y-connected machine will have a phase voltage that is only about 58%, 1 divided by the square root of 3 of that value. This can make transformers and motors cheaper to manufacture and potentially more reliable over their lifespan. It's a subtle but important engineering detail that contributes to the overall efficiency and economics of our power grid, especially for long-distance power transmission. Of course, no system is perfect, and the Y connection has a couple of disadvantages. A major one is its reliance on the neutral wire. If the neutral connection is lost or broken, the system can become very unstable, especially if the loads are unbalanced. Without the neutral to keep things in check, the phase voltages can fluctuate wildly, with some becoming dangerously high and others dropping too low. This can easily damage or destroy sensitive electronic equipment. Another drawback is simply the need for a 4th wire. In some applications, like long-distance transmission lines, the cost of an extra conductor can add up, making a 3-wire system more economical. Section 4. Y in the wild real-world applications. If you want to see a Y connection in action, you don't have to look far. Just step outside and look up at the utility poles that line our streets. The power distribution systems that bring electricity to our neighborhoods almost always use a 4-wire Y connection. You'll typically see 3 main power lines running along the top of the pole and a 4th lower neutral wire. This setup allows the utility company to deliver high-voltage power efficiently over distances, and then easily tap into it to provide the single-phase power that our homes use. It's the standard for residential and commercial power distribution because of its safety and flexibility. Transformers are another place where Y connections are essential. A transformer is a device that changes the voltage of electricity up or down, and its internal coils, or windings, can be connected in several ways. The Y connection is a very popular choice for these windings. Sometimes only the secondary low-voltage side of a transformer is connected in a Y configuration to provide a neutral point for local distribution. In other cases, such as in large power substations. Both the primary, high voltage, and secondary windings might be connected in a Y, creating what is known as a Y-Y transformer. This is common in high voltage transmission systems. The reason Y connections are so common in transformers serving our homes and businesses is that they provide that crucial neutral point. When a transformer steps down voltage for residential use, the Y secondary gives us two different voltages. For instance, it provides the 120 volts needed for our wall outlets, measured from one line to neutral, and also the 208 or 240 volts needed for larger appliances like ovens and dryers, measured between two lines. This dual voltage capability, originating from a single transformer, is what makes the Y connection the go-to choice for final power distribution, making it both practical and efficient for our daily needs. From the massive generators at power plants to the final transformer on your street, the Y connection is a fundamental building block of our electrical world. It's used in power transmission to safely move electricity over long distances and in local distribution to provide the flexible, multi-voltage power required by everything from industrial factories to our homes. Its combination of a stable, groundable, neutral dual voltage outputs and relatively simple current characteristics makes it a reliable and versatile workhorse. So next time you flip a light switch, you can appreciate the clever engineering of the Y connection working silently behind the scenes to power your world.
Have you ever wondered how we get so much power to big machines and entire factories? A lot of it has to do with something called a three-phase system. One of the coolest ways to set this up is the delta connection. So what is it? Imagine three electrical sources or phases that we need to connect together. In a delta connection, we link them end to end, forming a closed loop. If you were to draw it out, it would look just like a triangle. That's why it's named after the Greek letter delta, which is shaped exactly like a triangle. This simple but powerful shape is the key to how it works and what makes it so useful for heavy-duty jobs. Let's build one in our minds. Think of each of our three phases as a long wire with a start and a finish. Let's call our phases Phase A, Phase B, and Phase C. To create the delta connection, you take the finish end of Phase A and connect it to the start end of Phase B. Then you take the finish end of Phase B and connect it to the start end of Phase C. To complete the loop, you connect the finish end of Phase C right back to the start end of Phase A. Now you have a continuous, closed triangular circuit. There are no loose ends hanging out. Everything is connected in a self-contained loop, which is a very important feature of this system. So how do we get power out of this triangle? We attach our main power lines, called line conductors, at the points where the phases meet. These connection points are called nodes or junctions. Let's say the point where Phase A and Phase C connect is our first junction. We'll attach a line wire there. The point where Phase A and Phase B meet is our second junction, and we attach another line wire. Finally, the spot where Phase B and Phase C join becomes our third junction, with our third line wire. These three lines are what deliver the electricity from our delta system to the machines that need it. This triangular setup is not just for fun. It's designed for specific, power-hungry applications. You will most often find delta connections in industrial settings, where there are large electric motors that need a lot of power to get started. They are also very common inside certain types of transformers, which are devices that step voltage up or down for power transmission. The delta configuration provides a robust and reliable way to deliver a large amount of balanced power, which is exactly what these big pieces of equipment need to run efficiently and effectively day in and day out. It's truly a workhorse of the electrical world. Now that we know what a delta connection looks like, let's talk about the rules of electricity that apply to it. There are two main things we need to understand: voltage and current. Let's start with voltage. In a delta system, we have two types of voltage to consider: phase voltage and line voltage. Phase voltage is the voltage across a single phase winding, one side of our triangle. Line voltage is the voltage measured between any two of the main line conductors coming out of the junctions. Here's the simple and most important rule for delta: the line voltage is exactly the same as the phase voltage. So, we can write it as an equation: line voltage equals phase voltage. It's that easy. This unique voltage relationship is a defining feature of the delta connection. Because the line conductors are connected directly across the phase windings, they see the exact same voltage potential. Think about it. The line wires coming from junction A and junction B are connected to the two ends of the phase winding between them. There's nothing in between to change the voltage. This is incredibly useful in applications where you need to maintain a high, consistent voltage level to power your equipment. It simplifies calculations and ensures that the full voltage of the source is delivered directly to the load without any reduction. What about the current? The current behaves a little differently. Just like with voltage, we have phase current and line current. Phase current is the amount of current flowing through one of the individual phase windings, again, one side of our triangle. Line current is the current flowing through one of the main line conductors that goes out to the machine. In a delta system, the line current is always higher than the phase current. The rule is that the line current is the phase current multiplied by the square root of 3, which is about 1.732. We write this as line current equals square root of 3 times phase current. Why is the line current higher? It's because at each junction, the current from two different phases comes together. The currents from two windings combine to feed into a single line conductor. However, because the phases are out of sync with each other, by 120 degrees to be exact, they don't simply add up. The mathematical result of this combination is that the resulting line current is 1.732 times greater than the individual phase currents. This higher line current is a key characteristic to remember when designing and protecting a delta-connected system, as the wires need to be thick enough to handle it safely. Every system has its strengths and weaknesses, and the delta connection is no exception. Let's start with the good stuff. One of its biggest advantages is its reliability. Since the phases are connected in a closed loop, if one of the three-phase windings in a delta transformer fails, the other two can still deliver three-phase power. It won't be at full capacity, of course, but it can keep things running in an emergency. This is known as an open delta or V connection. Another great benefit is that delta systems provide a higher starting torque for large motors, helping them get up to speed quickly, which is crucial in many industrial processes. Another key advantage is that the delta connection does not have a neutral point. The system is made of just the 3 hot wires. This can be a benefit in balanced 3-phase-only industrial environments because it simplifies the wiring. You only need 3 conductors instead of 4, which can save on material and installation costs. This lack of a neutral wire is perfect for loads that are perfectly balanced, meaning each phase is drawing the same amount of current. This is often the case for large 3-phase motors or heating elements, which are the primary users of delta systems anyway. Now, let's look at the not-so-good side. That missing neutral wire can also be a major disadvantage. Without a neutral, you cannot easily power single-phase loads. Most of our everyday appliances, like lights, computers, and small kitchen gadgets, are single-phase and require a neutral wire to complete their circuit. This makes a pure delta system unsuitable for residential buildings or commercial offices where you have a mix of single-phase and 3-phase loads. The system is really specialized for machines that use all 3 phases equally and don't need that neutral return path. Another drawback is the higher line current we talked about earlier. IL equals the square root of 3 times IP. Because the line current is 1.732 times greater than the phase current for the same amount of power, the conductors used for the lines need to be thicker and more robust. This can increase the cost of the wires. Furthermore, delta systems can be more sensitive to unbalanced loads. If one phase starts drawing significantly more or less current than the others, it can cause voltage instability across the system, which is not ideal for sensitive electronic equipment. It really shines best when everything is balanced and symmetrical. So where can we actually see these delta connections in action? Their unique properties make them perfect for certain jobs in the real world. One of the most common applications is in large industrial electric motors. Think about the giant motors that run conveyor belts, pumps, fans, and heavy machinery in factories. These machines need a huge amount of torque, or rotational force, to get started. The delta connection's ability to deliver high, consistent voltage helps provide that powerful starting kick, making it the preferred choice for this kind of heavy lifting in the manufacturing and industrial sectors. You'll also find delta connections playing a crucial role in our power grid, specifically in high-voltage transmission networks. When electricity is generated at a power plant, transformers are used to step up the voltage to extremely high levels for long-distance travel. This is done to reduce energy loss along the power lines. Many of these large power transformers use a delta connection on their high-voltage side. The system's robustness and efficiency at handling high voltages make it ideal for the task of moving massive amounts of power across the country before it is eventually stepped down for local distribution. A third very common place to find a delta setup is inside the windings of a transformer itself. Transformers often have different connection types on their primary or input and secondary or output sides. A very common configuration is a delta Y transformer. In this setup, the high-voltage primary side is connected in delta to handle the incoming transmission voltage. The secondary side is then connected in a different configuration called a Y or star, which does have a neutral point. This allows the transformer to supply power to both three-phase industrial loads and single-phase residential loads, giving us the best of both worlds. From the factory floor to the power lines crisscrossing our landscape, the delta connection is a fundamental building block of our modern electrical infrastructure. While you might not see the triangle shape directly, its principles are hard at work every single day. It's a perfect example of how a simple geometric design can be harnessed to perform incredibly powerful and essential tasks. So next time you see a large industrial motor or a big electrical substation, you can be pretty sure that a powerful little triangle, the delta connection, is working silently behind the scenes.